Students, this session is a continuation of the impulse function in circuit analysis, and here we will consider the case the impulse response due to the impulsive sources. Okay, so first of all, impulse sources. The impulse function can occur in sources as well as responses, and we have discussed about the impulse responses, and now we will consider the sources which contains the impulse function. So such sources are called impulsive sources. That means impulse function when occur in the sources, and such sources are called impulsive sources. An impulsive source driving a circuit that imparts a finite amount of energy into the system instantaneously. And here figure shows an impulsive source, that means the source contains an impulse function del of t. And here it is an impulsive voltage source, and it has a strength or amplitude V0 volt, and it is applied to a series circuit connection which is containing resistor and an inductor L. When the voltage source is applied, the initial energy in the inductor is 0. That means we are assuming that initial energy in the inductor is 0, and we are applying this impulsive source to the series connection of resistor and inductor. Since the initial energy stored in the inductor is 0, so the initial current through the inductor will be equal to 0. That means there is no voltage drop across R. See, here there is no current through the inductor, means most of the voltage will appear across this inductor. So at that moment there will not be any voltage drop across this resistor R. That means when the current is 0, that means it will act as an open circuit. So the complete applied voltage will appear across this inductor. So there will not be any other voltage appear across this resistor. So the impulse voltage source appears directly across the inductor L. An impulse voltage at the terminals of an inductor establishes an instantaneous current, and this current will have the form I will be equal to, you know that what is the equation for the current through the inductor? I will be equal to 1 by L into integral 0 to t V0 into del of x into Vx dx. Okay, you know the equation for that is V into dx, that is equal to, here V is V0 into del of t, and here we are using the variable as x, so V0 into del of x into dx. So if we are integrating the del of x from the interval 0 to infinity, we will get the value equal to 1. So this integration will give the value 1 by L into this will be equal to V0. So I will be equal to V0 by L. So for an infinitesimal amount, the impulsive voltage source has stored in the inductor. That means the energy stored in the inductor, we know that the equation for the energy stored in the inductor, that is energy W will be equal to 1 by 2 into L I square. Here we know that I is equal to V0 by L, so we will get energy equal to 1 by 2 into L into, instead of I square we are writing V0 by L all square, that is equal to 1 by 2 into V0 square by L joule. That means the current V0 by L decays to 0 in accordance with the natural response of the circuit. We know that in the case of an RL series circuit, the natural response will have the form of, we have the general form, that is V0 by L into e raised to minus t by tau. So this is the natural response of a series RL circuit. So here we know that the current will decay in the form of an exponential. That means it will exponentially decay to 0 value. So in the case of this circuit also, when we are applying an impulsive input to a series RL circuit, the current will decay by the equation I is equal to V0 by L into e raised to minus t by tau into u of t. Here tau equal to L by R. That is the time constant. See here, the same circuit can be solved by using the Laplace transform method. So for that we have to draw the corresponding S domain circuit, and in the case of S domain circuit we have this circuit as like this V0 into del of t. So here an impulse comes, so the S domain value for this circuit will be V0, that is equal to V0, and that means V0 comes here, and instead of R here R will comes, and instead of L, that means instead of inductor there comes SL. Here there is inductor, instead of L it will have a SL. There is no initial charge on this inductor, so there is no voltage source associated with this inductor in the S domain equivalent. So this circuit will be replaced by the S domain equivalent like this. See, V0, R and SL. Since it is an impulsive source, the corresponding S domain equivalent is V0. So when we are considering this circuit, let I be the current flowing through this circuit, then we can write the equation for IS. I will be equal to total voltage by total impedance or total resistance, that is V0 divided by total impedance is R plus SL, that is equal to R plus SL. So in this we can take L outside, so you will get V0 by L into S plus R by L. If you are taking the inverse Laplace transform of this I, you will get the time domain value of the current. So time domain value of current I will be equal to V0 by L into e raised to minus R by L into t. That will be equal to V0 by L into e raised to minus t by tau into u of t. So this is similar to the previous equation, that is a natural response of the RL circuit. So in the case of an impulsive source, you can find that equation for the time domain current from the Laplace transform method by using the time domain equivalent circuit. And here you have to understand one thing, that here the current will decay in the form of a natural response of the series inductor circuit. That is, current's equation is time domain value of the current equation is V0 by L into e raised to minus t by tau into u of t. So that's all about this topic. Thank you.